All right. Let me use this paper to cover up some portions of this. I don't want you to get too far ahead of me. All right, ladies and gentlemen, let's talk about friction a little bit more deeply. This is an incredibly complex topic, actually, believe it or not, even though, everything basically that I'm going to teach you is old stuff from like 100 years ago. In fact, some of the stuff I'm going to show you right now is from almost 400 years ago. People figured this out. But even today, people still, they still investigate friction because it's just quite a complex thing as to what causes the frictional force between two surfaces. But ultimately, one of the things is the irregularities in the surface. And so I'm going to kind of be going back and forth on my screen. So what you're seeing is a little different than what's going to be in the video. I'm going to go back and forth between this screen down here and between the camera, which is looking directly at my face. And so the irregularities in the surface, when you look at like glass, for example, you might look and say, wow, that is really smooth. Like I can feel it. I can feel how smooth the surface is. But it's not. It's not. That's just a fact. The glass is made up of tiny atoms. The atoms are roughly spherical. So even if the atoms are super tiny, if you get down small enough, you will see little levels where there's a smooth surface, but it's all little round spheres. And you can see the little undulations of the surface. That's the atoms themselves. But even if that weren't the case, the atoms don't just form perfectly flat surfaces. This is really unusual. It's not impossible. It's not impossible, but it's very unusual. And so if you could look at the surfaces like really close, like make yourself as small as an atom, it would look like a mountain range to you. It wouldn't look smooth. That glass would look like a series of hills and valleys, irregular and all jagged, and it's not nearly as smooth as you think. Now it's relatively smooth. It's smoother than other surfaces, certainly, but it's not perfectly smooth. And that's where some of the friction comes from, is that irregularity in the surfaces. So I'm going to switch so that I can see myself a little bit better. I'm going to pin this screen. Can I pin that screen? I think I can. There we go. Okay. So imagine the irregularities in the surfaces. So when I bring two surfaces together like this, they're going to come like this, and then they're going to kind of settle down into little irregularities like this. So as I try to move my top hand to the side, it doesn't want to move very easily because I have to actually move up over that, and now I can slide across the top. And so that's a really important aspect, is that when two surfaces come down together, you can't see it. You don't see it settle down. It's not like it's moving like maybe only the width of a few atoms. So it's not a huge amount of overlap. But there is a small amount of overlap in certain places where the two kind of dig down into each other. So as you move sideways, there's actually a small normal force between my two fingers right here that is preventing them from moving. I need to move them and they'll start to slide upward. And then once that happens, it's going to get a lot easier. And that's one of the really important things to understand about the frictional force. There's actually two kinds of friction. The first one is the one we're talking about right now, where things are not allowed to move. Once they start to move, they move very differently. Like the dynamics changes a little bit. So let me switch back to my other camera here. Good. Okay. The second thing is that although you don't really see it very easily, the entire universe that you see around you in your room right now is actually only made of three particles. And those three particles are the proton, the neutron, and the electron. I mean, just think about that for a second. I mean, I don't know if you guys have ever really just sat and thought about it. Everything you see in your room right now, including stuff you can't even see like the air, is made of nothing but three particles. The three particles combine together to form almost like little solar systems. Every atom is like a little solar system with the nucleus of its very positive charge and the electrons, which are buzzing around it at super high speed, sort of forming like a cloud of negativity around it that is canceled out by the positiveness of the nucleus. So when you're outside of an atom and you look at it, it's neutral. It hides. It conspires to hide the secret, incredible electrical nature. I'm not saying that electricity is similar to atoms. I'm saying atoms are made from electricity. That is what the electrons are. The electrons are what is in electricity. And so even though the world conspires to hide the secret electrical nature, except for just every once in a while, you get a little shock or you see a lightning strike or something like that, every once in a while the world reveals to you, oh yeah, there are electric charges. But for the most part, it hides it from you. But if you can make yourself very small, make yourself as small as an atom and walk along the surface, you would see like, oh, you know what? There are places where it feels more negative and some places feel more positive. Overall, overall it's neutral. But yes, if you get very small and you work your way down along the surfaces, you'll see that because of the way the electrons are organized and because of the way the atoms are connected together, there are spots that feel a little bit more negative and some spots feel a little bit more positive. And those positive and negatives are drawn together. So when the atoms are far apart from each other, you don't notice it. But when they get close to each other, like within maybe the width of an atom, all of a sudden little electric forces start to become really significant. And that is part of the frictional force. So those two things combine together. So just to make it maybe a little bit more clear, let me draw a picture for you of these two surfaces. So let's imagine we have maybe a block of wood. And while when you look at the block of wood, it might seem like that bottom surface is very smooth and flat, but if you could look at a microscopic level, you would see no, it is definitely very irregular. And when I sit it on the table, you can see that there are places where, for example, look at this little spot right here. If I try to slide the top block to the right, you can see there's a little hill right here, a little tiny hill. That guy's going to have to push up over the top of that hill. Then I imagine that when this guy gets over to here, it's going to have to push up over the top of this. So that's the irregularities in the surfaces contributing to friction. But where does the electric force come in? Not here. There's no electric force here. These guys are too far apart from each other. They can't feel the atoms across the gap, but right there, they're in contact. I know this might seem weird, but when you put your hand on the table, there's probably no more than maybe about 15% of your hand is actually touching the surface. The atoms are actually touching. It's probably less than that. It's really difficult to get that much surface area of your hand in contact with the table. But the more contact you could make, the more frictional force that there will be, of course, because more electric force and also more the irregularities are digging in a little bit more deeply. And so that's going to increase the frictional force. So that's the origin of friction as we understand it today. Now that may evolve a little bit. Maybe we'll have a little deeper understanding at some point in the future, but right now that's our understanding of friction. Now, this is something that's a little bit more solid. There are two types of friction. So static friction and kinetic friction, and it has to do with those irregularities again. So static friction is okay, so static friction is the friction that you must overcome if you want to start something moving. So let's imagine that you had like let's say a sofa in your house and you just want to slide it across the floor to a new location. When you first start to push on it, you'll feel that there's a little bit of force. It doesn't start moving right away. So what do? You push harder. And eventually, as you push harder and harder, it's not moving, and then all of a sudden it moves. And I just want you to think about that situation where you moved something that was really heavy and you pushed on it, and it was really difficult at first, but once you got it moving, it became a little bit easier. So remember, and I'm going to switch my screens for just a second. This is really tedious. It's annoying that I have to do it this way, but so remember, the little things are going to dig in a little bit and they have to move like this. That's the static friction. You got to get this thing to move so that it moves up like this until they're kind of riding across the tops of those little, for lack of a better word, those little mountain peaks, right? Those little stalagmites and stalactites they're just kind of sliding across each other. But as soon as it stops, they're going to settle back down. As soon as you stop moving, the atoms will settle back down. They'll try to find like a little place where they can kind of dig in a little bit to each other. And now you're back to the static friction. So when you're sliding, the atoms are farther apart because look, my hands are closer together now than they are now. So some of the electric force has been reduced. Also, I don't have to slide. It's easier to slide over the tops now. That's why when you go to kinetic friction, the friction where things are actually sliding past each other, the force drops down. And I swear you must know that. You must know that you could not have gotten to be 16, 17, 18 years old and you've never experienced something where you pushed it and it was hard to push, but once it started moving, it was like you could feel it. You could feel it give way. You can literally feel the force dropping to the lower force. So the static friction is always the most because the atoms are the closest and they're the most interlocked, And once you go to kinetic friction, where everybody is sliding past each other, the frictional force is reduced. And that's because the irregularities are not interfering as much with each other, and the atoms are now farther apart, so the electric force has become a little bit weaker. It's significant. It could be 50, 60, 70% reduction in that frictional force because of the fact that you're sliding instead of static. Static meaning stationary. The objects are not moving. So let me flip back and let me give you the rest of this definition. There we go. Okay. I'm sorry, like I'm doing things so that the video is going to show nicer for you guys. All right, so for kinetic friction is the friction the word kinetic means moving. Um, when you take a class in PE, it's called kinesiology because it's the motion of the body. It may also be referred to as sliding or dynamic. And I am going to give you some other videos to watch. And so I just want to point that out because one of the videos that I like the most, this guy also uses the word kinetic, and it's called Flipping Physics. You guys should definitely check it out. This guy is like a really good teacher, better teacher than I am, frankly, and he has great videos to help you out. He also refers to it as kinetic, so that was really nice. I was glad to see he did that. But it's just as right to say dynamic or sliding. I don't like using the word sliding because it has the same letter as static. So now if I want to symbolize them, I can't just use the letter S because now the letter S could be static or sliding. So I'm going to use the letter S to indicate static friction. I'm going to use the letter K to indicate kinetic friction. Okay, so let's talk a little bit about what causes the difference between these and how does that actually play out. Okay, so this is like a basic principle that I for sure want everyone to know, and it's very relevant to driving. It's very relevant to what we're talking about with cars. So that is the static friction is always less than the kinetic friction. Now, depending on the surfaces, sometimes the static friction might only just be a little bit more, just maybe 5 or 10% more. But in most cases, the static friction is probably closer to between 30 and 60% more than the kinetic friction. It's not a small difference, it's an enormous difference. So if you think about when you're driving in a car, remember, we cannot move unless we have friction, right? If you're on an icy surface and you try to walk, you don't walk very fast, right? Because you can't exert very much force. There's so little force between your feet and the ground, you just can't propel. It's impossible. It is literally impossible for you to speed up quickly. Now you can speed up a little bit, but you can't speed up quickly. So when you're driving in a car and you're thinking about, okay, well, if I want to turn, or if I want to speed up, or if I want to brake, which of the two frictions do I want to use? Do I want to use the static friction or do I want to use the kinetic friction? Duh, I want to use the static friction. It's like going to give me 50% more power because it's going to give me 50% more force between the tires and the road. So I always, 100% of the time, want to be using static friction. Now, when would I want to use kinetic friction? If I was drifting, if I wanted to skid on my bike, if I lock up my back tire and I want to skid and slide, then I want the kinetic friction. So all I want to do, I don't want to go over everything today because it's a lot to think about and I want to give your brain time to process this. But I do want to plant this in your mind, this idea of the car tire, because it's very relevant to what we're talking about when we're talking about the storyline and just in general about forces. So let me draw a picture for you. And just so you guys understand, the reason why I'm pausing is because I know that if I don't look at my camera, then the sound quality is bad. So I'm going to be quiet for a second while I draw the picture, and you should be drawing the picture too. Okay, so here's our car tire. Oh, perfect. I'm going to have just exactly the amount of time I wanted to have left. The car tire is moving to the right. It's rotating in the clockwise direction. When the tire rotates in the clockwise direction, imagine the bottom of the surface down here. When it gets down to right here, the tire is moving this way, so it's going to exert a force on the road in the backwards direction. Think about which law. Which law says that the road's going to push back? The third law. The third law says the tire will push on the road will push back. So now the question is, when the tire is rolling, I want you to just take 15 seconds to think about this. When the tire is rolling, the car's just driving on the highway, everything feels totally normal, nothing exceptional is happening. Is that the static friction or is that the kinetic friction? Just take 15 seconds in your mind and just play it out. Is it static or is it kinetic when the wheel is rolling? Okay, guys, are you ready for the big answer, the big reveal? You can, in your own mind, just kind of self-assess. Did you get this one correct or not? The answer is static. And I know because the tire is moving, it feels like it must be kinetic because the tire is moving. But look, I'm going to switch my camera for just a second so I can demonstrate it a little bit better. Just give me a second here. Okay. There we go. Pin. Yes. Okay, look. When the tire is rolling, look at my hands. Are my hands sliding past each other? That's going to be kinetic friction. If my hands slide like this, when the tire rolls, there's no sliding. There is no sliding. The two surfaces are not sliding past each other. When the tire rolls, that is actually static friction because the two surfaces are not sliding past each other, which is the requirement for kinetic friction. So as long as the tire is rolling, you have the static friction. So just imagine, if you wanted to accelerate, you would get better acceleration from using the static friction because it's going to be more force. What if you want to brake? You do not want to slide. That's why anti-lock brakes exist. It's so important. Static friction is so much stronger than kinetic friction. You do not want the tires to slide. So you can hit the brakes and slam on the stop the tires and they'll slide and you will come to a stop, but you could probably come to a stop about anywhere from 30 to 50% less distance if you keep the tires rolling, but it's really difficult for people to do. I mean, it takes professional drivers to be able to do that. So the car designers decided, you know what, an average person just can't do it. They just can't get that maximum braking power because they just can't push the brake down to the border of almost sliding. Most people just don't have the, they just can't, don't have the wherewithal to be able to pull it off. So they said, we'll have the car do it. When the car tires start to slide, the brakes will take over and they will prevent the tires from sliding so that you can brake with a greater force and come to a stop with less distance. So it is very relevant. If you guys watch drag racing, which I'm sure you don't, I'm sure nobody in here watches drag racing. Give me a thumbs up if you watch drag racing, but I know I'm not going to get too many thumbs up here. If you look up on YouTube, funny cars, that's what I would look up. Look up the funny cars. Or you can just look up drag racing in general. You will see that before the race, the drivers spin the wheels. So that's kinetic friction. They're sliding the wheel against the ground. And you might think like, well, that's obviously they're sliding. Look, I can see the smoke. When you see smoke coming from the tires, that's kinetic. When you don't see smoke, that's static because the tires are not sliding. You see the smoke when the tires slide. So you see at the beginning of the race, they're spinning their tires and there's like huge clouds of smoke coming up. But the reason they're doing that is because they want to heat up their tires. They're trying to heat up the tires. Don't you know that? Don't you know when you rub your hands together, it makes them warm? So they're trying to warm up their tires by using friction to convert that work that they're doing into heat that makes their tires warmer because it turns out that warm rubber digs down into those little grooves, into those little irregularities a little bit better. So soft tires have better grip than warm tires or than cold tires. So they're just trying to warm their tires up. That's all they're trying to do. But if you watch the actual race, that's the important thing. Watch the actual race. You will see there's not very much tire spinning. And whoever wins is usually the first person who can get their tires to stop spinning, they're going to win. Because as soon as their tires stop spinning, they're going to go to the static friction. And now they're going to get about a 50% increase in the amount of force that they can exert, and therefore they're going to accelerate faster than the other car. So the spinning the tires might look cool, and you think, oh, that looks like, but that's just people ruining their tires, and there's no benefit to it at all. Nobody racing wants to see smoke come off their tires. If you see smoke coming off your tires, it's because you're losing the race. So you want those tires rolling. You will accelerate faster, you will brake faster, and you will be able to turn with a sharper turn as long as those tires are not sliding. Okay, so that leaves us about 15 minutes left in class. What I'm going to ask you to do with that remaining 15 minutes, because I want to move away from this, and we'll talk about it just a little bit tomorrow. about 15 minutes tomorrow, and we'll be done with it. And then I'll give you the rest of the time tomorrow to continue working on the storyline activity with Whiplash. So what I want to see today is that by the time you come into class tomorrow, everyone's done with the document. You've read through it. It's not perfect, but it's your best understanding as you were able to read and see and watch the videos. It's your best understanding right now at the moment. And you'll use that information tomorrow to start writing your CER. And I really want it to be done in class. I don't want this to be homework. So please use this time right now to continue reading, watching the videos, and then tonight, if you could please make sure that you have all those questions answered up to the end of page 4, then tomorrow you can write your CER and you'll be done in class, and this will be a nice boost to your grade. Okay, so let me stop my video here.